Hello everyone, welcome to another lecture series. In this series, today we are going to discuss about Master's theorem. So basically, we will start about how to solve a recurrence relation, how to find time complexity of a recurrence relation. For that, the Master's theorem is used. So today we are going to learn about what is a Master's theorem and with some examples, what are things or what are the notation associated with a Master's theorem and so on. Okay, so let's start. So as the first line suggests, it is used to compute the time complexity. Okay, time complexity of a recurrence relation. So what does a recurrence relation mean? If you remember the previous algorithms that we talked about, the merge sort and quick sort, in both the merge sort and quick sort, you can see this is the same thing that has been repeated. So this is the same function that has been repeated. If you remember this, but when we discuss about the previous lecture about the merge sort, then we discuss about how these things can be related. So these things are marked on, and same for quicksort. This is the function that has been called. So it is recursively called. So that type of algorithms where the function is being called again and again by the same function, that kind of functions are known as recursive algorithms. Part of it. We have discussed one another algorithm also. If I have it, yeah, we have discussed this algorithm, insertion sort algorithm also. But in the insertion sort algorithm, if you remember, uh, there is no function that has been called again and again and again. If you remember this algorithm, there is no function that has been called again and again. It's just one step function. It will copy some variables to other. It has some kind of looping condition that will be followed. So that's how it plays it. But in case of these two functions that we are talking about, the smart sort and quick sort, the same function has been repeated. So to find a time complexity of this kind of function, master theorem has been used. So this is kind of iterative algorithm, but these two functions are recursive algorithm. We also have stated we have given an equation t equal to something and stated using master theorem we can solve it. But today we are going to see how master theorems can able to solve this part of it. And master theorem cannot be applied to any random recurrence relation. It should have some particular format to which it can be applied to. Okay. So this is a particular function that is there. So this is a form of a particular function. What does Tn equal to a Tn by b plus f of n? Now let's understand the terms one by one. Tn is a recurrence, total recurrence relation denoted by Tn. A is the number of subproblems. So A is the number of subproblems and n is the size of the input. So if you remember this part, we have discussed that this is T for this part. We have discussed this is Tn by 2 and this is Tn by 2, and there are two sub type of problems are there. So 2 into Tn by 2. So here this 2 as I refer to as A, so the number of sub problems are 2, and n by b, so it is this n is the size of the input, so depending on how much, if it is 4 then 4 by 2, that kind of one, and the size of each subproblem. So size of each subproblem, if you divide it into both equally, if it there is a 6 inputs, so if you divide them into half part, let's say there are 6 inputs are there, and 1 3 and 6, so if you divide them, if you take a 3 and divide them into t3 or t3, then both equally, then this is the size of each subproblem. So this is the size of one subproblem, this is the size of another subproblem. That's how we define the size of each of the subproblem we define. Then we move to the next part of it, that is Fn. Fn is the cost of the work done apart from the recursive call. So apart from the recursive call, see, there's also a function called merge. So this is the function that we are supposed to take on in the merge sort. This is the merge sort merge one, and this is the partition one. There is the extra thing that we are taking upon. We said that while doing this, we said that this is takes an time complexity of order of n times, and same as this takes an time complexity of order n times. So we said that this particular function that has been called extra apart from this recursive calls, that is the cost of the particular function. So Fn is the cost of the work done apart from the recursive call. I hope you get this particular point of it. So that's why we write as 2 of n plus, okay, I just wrap it and again write it down. Okay, what was the, before both the one, the same one was there. It was 2 into t of n by 2 plus order of n. So 2 is the number of subproblems, n is size of the subproblem, and it is order of n. In this, in there, it is the, for quicksort is the base case thing, and for merge sort both are the same for the best and worst case. But in worst case, quicksort has a random one, but we stick to this particular one itself. So to make it simple for both the algorithms for understand. So yeah. So again, I'm repeat. This is the Tn. A is the number of subproblems. N by B is the size of each of the subproblem, where n is the number of input. Fn is the cost of the work apart from the recursive call. If any extra work is done, so that is the cost. Now these variables, there are some constraint about the range of this particular variable. A should be strictly greater than or equal to 1. B should be strictly 1, and both are constants. And Fn should be a positive function. So what does a positive function mean? Is that uh, if you take sub, if any, let's say if you have a function and let's say is a fx is a function, and how can you say fx is positive or not, positive function or that the range of this particular function should always be positive. So even if the domain, that is the values that the particular x can take, it can take any value, it can take positive value, it can take negative value, but the range should be the positive one. So the outputs, that is the y value. So we always know we have a set of domain here, and from domain we map it to the range. So that is the mapping, and how this mapping is done, given by an x function. Let's say we define an x function of, let's say, 3x square plus 4. That kind of function we define. So this function, in event of x, whether you take x equal to 2 or x equal to minus 2, or x equal to 100 or x equal to minus 100, in both the one you will get always a positive value itself from f of x. So that kind of particular function are always known as positive function of it. That means you are doing some work, positive work, because if you are taking negative, that means a negative work we are not considering. We are always taking the positive work, or the positive functions we should be able to take. So this sign should be positive. So this particular form, when it has a, when if any algorithm comes up in this particular form, we can use a Master's theorem to quickly find the time complexity of it particular part. I hope this particular one is clear. Then we move to the, we actually simplify this in more way so that we can get the time complexity in more easy format we get. So we take this particular one while we solve the particular problem. We take some problem also and define how it is solved. But for now, Tn is the same. A, this number of subproblems. T n by b is the how many size of each of the subproblems, where n is the number of input. Then this particular function fn we write in this particular order. So theta of n to the power k log p n. In this particular order we are writing this, and these are defined constant still there. A it should be equal to greater than equal to 0, 1. B should be greater than equal to 1 strictly, and k should be greater than equal to 0, and p should be real number. So this particular constant should hold when you are given one equation, and this particular constant should hold, then only you can apply this particular algorithm. There are three defined parts. We are actually focusing on a, b, and b to the power k. So in this, what can be there? Either this can be less than b to the power k, this can be equal to b to the power k, or this can be greater than b to the power k. This is the only three things that can be possible. So based on these three things, three different time complexity format, we can get it quite easily. Okay. Starting from one, let's start from, let's start this one. Okay. Huh. So starting from this one, you can see A is greater than equal to bk. If this particular one is satisfied, then the time complexity is written as theta of n log a base b. If a equal to b to the power k, then there are three different things we need to put consider. P greater than equal to minus 1, p is equal to minus 1, p less than equal to minus 1. If p is greater than minus 1, then this particular formula, equal to, then this, if less than, then this particular formula. It's quite similar to this one. That's it. Then if a is less than b to the power k, then again we are taking two condition of p is greater than equal to 0 and p less than equal to 0. Then these two formula is applied according to the p value of it. So basically this is the equation we are taking about. If this is the form of the equation we have, it's is the form of the first part, and there is a positive function we have. Then we just look on the values of a and bk. Depending on the values of a and bk, we retrieve the values of what is the time complexity that will be taken by the algorithm to run. So by time complexity, we mean that it should not be like it is working on NVIDIA in this, in AMD in this, in any Raspberry Pi it is taking on this, in any Android architecture it is taking this. Is not that. It is indefinite of the architecture. It is an estimate of time that will be taken to run that particular algorithm. So we can run it just we can find, like previously what we learned about, we can sort the algorithms in different way. Every algorithm, whether it is a quick sort, whether it's a merge sort, if you give an input of something, then the output will remain the same. But the time that will be taken by that algorithm is different. So while writing an algorithm or while writing a particular code, it's not that we just write code in some random order we get the output, but we need to write an efficient code to get that particular output. If the code is not efficient, that is, the complexity involved on a particular code is too much, then it will be very difficult for the whenever you deploy in any kind of architecture, that will take too much memory or it will take too much time to actually get the output. And now every time is at the time of we are doing at fast and real time, so we need the output too quickly. So even though if we have two choices of getting the output, we'll take that particular algorithm which takes less amount of time. And now how to analyze the particular time of the particular algorithm? Then we write some recursive algorithm, recursive relations. From that we find some time relation which is universally true. So we found that particular one. So that's how the why the time complexity is important to analyze, and what this is the theorem, why master's theorem we can use right now to solve this particular problem. So it will be quite helpful if we can take some example then to solve this, to see how this is solved. Okay, I will keep it in the right hand side of it so that while doing this particular examples, we can relate to this and see whether it's matching or not. Okay, okay. Let's start with this one. So let's take a simple example first of all. That, let's say T n is equal to 40 n by 2 plus log of n. Okay. Now, first of all, let's find out the values of a, b, p, k. Let's find out the particular values. Here, a equal to 4. You can see a equal to 4. B is equal to 2. Then k is equal to 0 because there is nothing. N to the power 0 is 1. So we know n to the power 0 is 1, which is here. So k equal to 0 and p equal to 1 since it is 1. Now, mm, since we get this particular value, let's compare A with BK. We compare A and BK. For that, that's A equal to 4 and B equal to 2 to the power 0. That means 2 to the power 0 is 1, is greater than 1. It falls under first category of 1. So it falls under the first category. So it falls under the first category of 1s. Now let's find the time complexity. So if it is a first formula, then what is the formula we have? We have this particular formula. So we have theta n, it will be in the upside, to the power n to the power log, it is a base b. So if we just put this particular one, it is theta n, b is log of a is 4, b is 2, and by using the formulas of logarithm, we can write it down as 2 log 2, and finally we will get theta of n squared. So this particular, if a reconciliation has a form of this, then we can find out theta of n squared. So by quickly analyzing it, we can get this particular formula. Okay, then go to the second example. Let's say we get the second example. Let's say t of n is equal to 25t n by 5 plus n. Let's find the formula. A equal to 25, b equal to 5, here and k equal to 1, here p equal to 0. Again, let's find a and b, k. So here we find 25, which is greater than 5 power 1. So again it fall under the category of first. So it falls under category of first. First discuss some examples of first, then we put the second one. Then according to the formula, what the formula says is that theta, it is n, it is log a base b. Okay. If we put here formula, it is theta, it is n, it is 5, it is 5, then again putting the theorems of logarithm, it is 5 square, it is 5 base 5, and log n base 1 is n, so n square. So this is the particular part. Yeah. So this is for this is time complexity that will be taken. Let's go to the third example. Let's say t of n is equal to 3t n by 2 plus n. Okay. Now a is 3, b is 2, again k is 1, and p is 0. Comparing with this, we get this. So again 3 is greater than 2t power 1. So a is greater than bt power k. So it falls under first. So theta of n log, what is a base b. So if we do this, we will get theta of n log a is 3, it is 2. Yeah, we get n log n to the power log 3 base 2. Let's take a fourth example. Wait, it's t of n is equal to 3t n by 3 root over of n. Whether it is false under this or not. Okay, let's check it out. If we take this here a equal to 3, let's a equal to 3, let's say b equal to 3, here n can be written as 1 by 2. So here n by 2 is k. So k is equal to 1 by 2. And we say k greater than equal to 0. So k equal to 0.5, we say greater equal to 0. That is fine. And p equal to 0. So it falls under this particular. So it is abide by the formulas and the constraint that it has. So we can write, now it fall under again the first one. So we can write a theta, what is that? N log a base b. So here we can have theta n log 3 base 3, which is 1, which is theta of n. This is the time complexity of the algorithm. Okay. So okay, let's move to some other category now. Which one? This is 4. Okay, now this is 5. Let's say we have t of n, and we take 90 n by 3 and n square. Okay, yeah. If we take this, there is a equal to 9, b equal to 3, k equal to 2, and p equal to 0. Now we need to find a and bk. Now here a is 9 and bk is 3 power square, which is equal to 9. So these both two are equal. So if it is equal, then it falls in the second category. Now for the second category, we need to see whether it is p value. What the p value? P is equal to 0. That means p is greater than minus 1. So this, since it is 0, so that now since 0, that is greater than minus 1. So it falls under the second category. Second also 2a. It falls under that particular category. Okay. Now what is the, if it falls under this, then the formula says is theta and log, first part is the same with uh, some other formula, that is log, here put log of p plus 1 into n. So this is the formula here. Let's put the values. Theta of n, so a is 9, b is 3, p is 0, p plus 1 is 1, then it is n. Okay. Then that means theta of n, this becomes 3 squared, so it is 2. It is 2 squared log of n. So apparently is theta of n squared log n. So this is how, for this particular one, this is the particular time complexity that it will take to run. And remember, like log of something, let's say to this is not equal to log of n this. So these two are not equal. If it is log, this is one only. So if you have let's say any other one, let's say it is, this is what is mean is as log of n. So that's how it is interpreted. Okay, okay, let's move to the second one. This let's take another example. T of n, we take 2 of t n by 2, and let's say take n, and that's it, n log n. Okay. Now here a equal to 2, b equal to 2, and sorry, this is k, k equal to 1, p equal to 1. Okay, this is how this is. And now if we take a and bk, if we just compare, then 2 is equal to 2 power 1. For the second category. And now this is, now we have to look for p. If we look for p, here p is equal to 1, so this is greater than minus 1, so it falls under 2 of a, so it falls under 2 of a category. So now let's find a time complexity. So what's the formula for it? Theta of n log a base b, then log p plus 1 into n. Okay, then theta of n, it is a base b, 2 base 2, b is 1, so 1 plus 1, it is n. Then this is theta, log 2 base 2 is 1, and this is log square n. This is the formula. And as I said, this should be written as log square n, should not be written as log n square. So this should not be written, these two are not equal. So many students sometimes get this particular confusion while writing this, so remember this particular point. Okay. Okay, so this some examples. Let's see some examples. Apart from this, let's say this is Tn. We take 0.5 Tn by 2 and 1 by n. Now here a is equal to 0.5, b is equal to 2, k, if you write n to the power minus 1, k equal to minus 1, b to the power 0. Now whether this particular falls under this or not. A is equal to minus 5. What is the condition? A should be actually greater than equal to 1. This is invalid. B is equal to 2. It is valid. K equal to minus 1 greater than 0. This is also not valid. And this is the last part. This is also not valid. And at the end, k equal to minus 1. This is also not valid. So even if I'm taking just checking out for any other not valid or not, if one is not valid, the entire thing is not valid. So this cannot be solved with master theorem. So since master theorem has some limitations, as I said, it cannot solve all the problems. And this is one of the problems where it cannot solve. Okay, let's say if we take Tn, where 6Tn by 4, and let's say n square log square n. Now this falls under this or no. That's before finding out this. This function, as I told, this should be a positive function. There should be a positive function, but here is a negative function. What does it say actually? So if we take this negative one, this has a particular implication. Why this should be a positive function out of it? So if we do some work and divide them into subproblems, then divide them into subproblems. So if we do some work, then divide to some subproblems. But here it's saying that if we don't do any work, it is divided into some subproblems. If we don't do, like it is negative, if we don't do some any kind of works, when don't again it's some negative, so then it becomes subproblems. That is not valid. So this kind of things this kind of one cannot be solved with master theorem. So as I said, the limitations are associated with the master theorem. So every problem cannot be solved with help of master's theorem. That's it. Let's go through some other example. This is 8. Okay, let's take 9. So at the end, we are going to solve that particular equation that is involved in the quick sort and merge sort. Okay. Okay, let's move to the 9 example. T of n, 3t n by 2 plus, let's say this is n square. Okay. Here a is equal to 3, b is equal to 2, then k is here equal to 2, p is equal to 0. Now let's compare a and bk. So a is 3, b to the power k is 2 to the power 4. That is this. So A is less than bt power k, that fall under the third category. Now if we take the third category, we need to see what the value of p. Now p is 0, that means it is greater than equal to 0. That means it falls under 3. This is 3 of A. It falls under 3 of A. Now let's find the time complexity. Now the formula is T of n is equal to theta of nk, nk log, it is p n. So it's theta of k is 2 log p. P is 0, 0 n. So in the log theta of n squared. So this is the form, time complexity of this algorithm. Let's move to 10 example. Uh, let's say T of n is equal to 2tn by 3 plus n squared. So here A is equal to 2, B is equal to 3, K is equal to 2, P is equal to 0. Now A and BK, if we compare, 2 is less than 3t power actually 2. So this is 1. This falls under third category and P is greater than 0. Then this falls greater than equal to 0. This falls under 3, 3a. So this falls under 3a. Now what is the formula of it? The formula is theta of nk log of pn. So theta nk, k is here too, log of 0, p is 0, n. So it's theta of n squared. This is the one of this time complexity associated with this particular. You can see in very short amount of time we can do this. Otherwise, I will explain some other methods which are also associated to solve this particular one. Iteratively, we can solve this, but without using that, we can quickly solve out this type of time complexity using this particular master theorem by using just a simple rules out of it. So if any equation falls under this particular format, you can use quickly the master theorem and find out the time complexity associated with that. So now let's say T of n equal to 3t n by 3 and n log of n. Okay, we take this one. So here this can be written as T of n 3n by 3 n log to the power minus 1 and this we can write it down, right? So here a is equal to 3, b is equal to 3, k is equal to 1, b is equal to minus 1. So a equal to 3 greater than minus 1, b equal to 3 greater than 1, k equal to 1 which is greater than 0, and p minus 1 which can be a real number. So it falls under category and the format is the same. Okay. Now here if we now see a and bk, so a, compare a and bk, so it is 3 and b to power 3 to power 1, so 3 is equal to 3. So that means it falls under 2. Now which one? We see p is equal to minus 1, so that means it falls under this is equal to this is minus 1, so it falls under 2b. So it falls under 2b. That's it. So if you find from this, let's find the time complexity of it. So as a formula for 2b, it is theta of n then log a base b, and it is written as log n. Okay. Now theta of n, what is a and what is 3 base 3 log n. Sorry, this should be here. Should be here. Yeah. Then this is 3 is 1 n log n. This is time complexity of this particular algorithm. Now let's go to another algorithm. Let's go take another example. Let's say t of n is equal to 8t n by 4, and then it is n squared and log n. Okay, so a is here is what? A is 8, b is 4, k is 2, and p is 1, right? And it's the same one, it falls in the same category. Then it is 8 and b to power 4 square, which is less. So this falls under the category of third one. And here p, if you see, if there are two conditions of p, so p is equal to 1, so it can equal to 0. So it falls under 3a. which falls under 3A category of it. So by this, if we take this particular formula, how we can find Tn? So Tn time complexity is theta n to the power k log Bn. So theta n. So k is what? K is 2, B is 1, so n. So this is the time complexity of this equivalence relation. Okay. So let's take last 2-3 examples. I hope now, if you do this continuously with some examples, this formula remain in your mind. So for the first time, it may seem that formula is complex, but now I hope by finding out, you can quickly find out which formula is related to which one, and just there is some small tricks like this is related to this one, except that this remain the same, like this and this remain the same. For this one, this remain the same. For this, so simple tricks you can put it down to remember this particular algorithm. But yeah, with some examples, if you do, then it much more get clear. And part if you do that thing instead. So here a is equal to root 3, b is equal to 3, k if you put here 0 because it is nk 3 power 0, and here p is equal to 1. Since a should be equal to 1, a greater than equal to 1, and 3 to the power 1 by 2 is greater than equal to 1, so a falls under this, b and k, everything falls under this itself. Now let's find a relation between a and bk. So a is root 3, b is 3, 3 power 0 is 1, that means this falls under root 3 is greater than 1. So root 3, 3 to the power half is anything, it will be just greater than 1, it will be greater than 1, etc. So it falls under the first category of it. So for the first category, what does it say? It says that theta of n, it is n for the first one. So n log a b. This is the formula. So theta of n, b a is root 3. This is 3. If we simplify a little bit of it, then it is 1 by 2 log 3 3. So it's the same one. It is theta half. So theta half means root over of n. So this is the time complexity of this one. Okay. Okay, let's take a last example and we'll find out. So let's take a simple example of it. T of n, 90 n by 3. So C of n. So this is the number of subproblems, size of the subproblems, and a positive function of it. That's how it is. So A equal to 9, B equal to 3. Here, if then K is equal to 1, B is equal to 0. C is a constant. So you can comment this out. If a function is order of n, you can write them as C of n times. Okay. Now, if A and BK relation, you can find 9 and 3 to the power 1. So this is greater than 1. This falls under the first category itself. So first category theta is n log b base a. So this is theta, and this is n. This is log a b base or a base b, a base b. Sorry, it is a base b. So a base b is 9 base 3. 9 base 3 is theta n 2 log 3 3. So n log n, n base n of log is n is 1. So this is how theta of n square. So these are the examples of the formula that we have taken. One formula examples we have done, and if you get this kind of reconciliation which falls under this category, then you can just calculate, find up a and b values. Some are not fall in the category of this. Find out whether it is satisfied or not. If it is not satisfied, then don't use this particular one. If it is not satisfied, is satisfied, then find out the a and b values depending on the criteria, or we can find out which one falls under this, and you can easily find out the time complexity associated with this one. I hope the examples becomes more clearer how to use a master's theorem of it. Now, as I told, this theorem is quite easy, helpful for maybe the one who is appearing for a competitive exam, or that kind of one that is also helpful, or for anyone who is actually analyzing time complexity of an algorithm. When you write a particular algorithm, then you can find it out, and this particular theorem is useful. And at the end, let's find this particular time complexity of this one, and how the last we have said, but here let's find the time complexity and see whether this is equal or not. Let's don't compare with one. We write this and let's find out if we can till now memorize the master's theorem or not. Either way, let's give it a try whether we can or not. Okay. So what was the one? This was the formula was yeah, the formula was okay. Something is wrong. What happened? There's something. Let me just try. Something is different. Okay, move on. From this, we are talking about the master's theorem to. Okay, yeah, some technical fault. Okay. Now, what's the formula that we are talking about? We are talking about T of n, this particular formula, and this particular formula can be related as 2Tn by 2 plus order of n. This is the formula we have. Now, if we can, let's find out the a, b values, a equal to 2, b equal to 2. Here we can write it down as constant. So 2, sorry, okay, again, why it is happening? Okay, okay, some technical faults are going on. Okay, now yeah, we can write it down as 2t n by 2 plus c of n. Okay, this can be written as this. Now here, if we find then k is equal to 1 and p is equal to 0. Now if we find bk, so 2, we find b and b to the power k. So it is 2, 2 to the power 1, so 2 equal to 2. So 2 equal to 2, that means it falls in the second category. If we find p equal to 0, that means criterion equal to minus 1. I hope you remember this. Then this is p equal to 0, p is greater than equal to 1, that the formula is this one. So the formula is what? Let's have a n log a is a base b, then log it is p plus 1 plus n. So if we apply this particular formula here, we will get theta. So theta of n log 2, this is p plus 1. So p is 0, p plus 1 is 1, n. Now theta of n log n. So this is what we have got when we have explained this particular theorem out of it. Now we have actually derived from Master's theorem how n log n was formed. At the time of saying, I said we can apply Master's theorem and get n log n, but now the time complexer Marshall is n log n. The base case time complexer Quixote is also n log n by this particular one. I hope these lectures give understanding of how we can apply Master's theorem, why time complexity is important to analysis in any algorithm we put down, and how it can be quickly solved with this Master's theorem. Okay, if you have any kind of doubt to say it out, then please drop in a message in the comment box. I'll try to resolve the doubt to the possible extent I can. And if you want some other topic that needs to be covered, just put down in the comment box section. I will try to make that particular video or the content of that particular video and put it live for you in possible extent of time.